So what I want to do is go over just some various problems that you might encounter on a polynomial exam. So here's the first one. This is a second degree polynomial. And usually what we want to find out from a second degree polynomial is we're interested in the y-intercept, the roots, and the vertex. Now, as far as the y-intercept goes, the y-intercept for this second degree polynomial and all these functions that we're dealing with, you're going to find the y-intercept by just substituting a 0 in for x. Because that's what the y-intercept is. It's where the graph crosses the y-axis, which is that's where the x is 0. So in this case, we get the point 0, 16. That's our y-intercept. And that's the easiest thing for us to find here. Now, another thing that we want to look at these x-intercepts, the roots. So here we've got x squared minus 10x plus 16, and we just set that equal to 0. So when we're trying to find the roots, what we do is we just take the whole function, set it equal to 0. In other words, we're setting y equal to 0. We're trying to find out where is this function equal to 0. Now, you won't always get x-intercepts. Sometimes you'll get non-real roots. You'll get numbers with I in them. In other words, numbers that are non-real but will make this function equal 0 when you plug in for x. For this one, I'm going to factor it because a lot of times that's a good way to solve these equations if you got something that you can factor pretty quickly. So in this one, I've got -8 and -2 are my fact, x minus 8, x minus 2. That means that x minus 8 equals 0 or x minus 2 equals 0. Remember, that's the zero product property. If two things multiplied together equals 0, then one of them needs to be 0. So we get x equals 8 or x equals 2. Either one of those. If x equals 8, f of 8 is 0. F of 2 is also 0. So these are the two zeros. Now in this case, they're also intercepts. So you've got an intercept of 8, 0 and 2, 0. It's where it crosses the x-axis. Now, as far as the vertex goes, we've got x squared minus 10x plus 16. And this is not in the form that we find most convenient to find the vertex. When we're talking about the vertex, usually we want a form that looks like this. We want, a x minus h squared plus k, because then we can clearly see the shifts. The shift, we've taken this function x squared and we've shifted it to the right h and up k. So the vertex is going to be hk. Now, because we don't have it in that form, we need to put it in that form. And the way we can do that is by completing the square. So I group my x's together and have the 16 on the outside. Then I take half of the x and square it. And I add a 25. Now, I can't just add a 25 like that. I need to counteract it by subtracting off the 25. So really, I've done nothing. Now, once I do that, once I take half of this x term, square it, and add it here, I'm guaranteed that I can rewrite this x squared minus 10x plus 25 as x minus 5 squared. See, x minus 5 squared minus 9. Because negative 25 plus 16. So here's my vertex. My vertex is 5, negative 9. Remember, you get the x coordinate of the vertex from the parentheses with the x, only it's the opposite. And the y coordinate you get from the end, and it's exactly what you see there. Okay, now that's a second degree polynomial. Now, we can move up to higher degree polynomials like this one that has the roots 2, 1, negative 5. So let's look at this situation. We're given roots here, 2, 1, negative 5, and a y-intercept. And let's suppose we want to come up with a polynomial that has these roots and this y-intercept. It has these x-intercepts and this y-intercept. Well, let's go here. We've got, if we want the roots, well, we can just write down the factors here. If we've got the roots, we can change those to factors. X equals 2 means x minus 2 is a factor. X minus 1 is a factor. And x minus a negative 5. Whoops, sorry about that. Had the paper down too low. Okay. Now, what we have here, we have a polynomial that has the roots 2, 1, and negative 5. Well, I want a polynomial that has those roots but also passes through the point 0, 20. So I'm going to put a little constant in the front here and solve for that constant to make this polynomial pass through 0, 20. And the way I do that is I'm going to put a 0 in for x and a 20 in for y. So I've got negative 2, negative 1, and 5. See, all I did was I just put a 0 in for x, and I've got a 20 in for y, and then I solve. Now, of course, this is going to give us 20 equals 10a, right? That means that a is equal to 2. So we've got our polynomial now. Our polynomial is 2, x minus 2, x minus 1, x plus 5. Okay, now let's move on down here. Let's look at another one here. Let's suppose that my roots are negative 2, and I'll use this to indicate multiplicity 1, M1. We've got 3 multiplicity 2 and 4 multiplicity 1. And we have the y-intercept 0, 4. So let's see what this is going to look like. We've got f of x equals, let's see here, I've got x plus 2, x minus 3, but multiplicity 2. So I'm going to square it, and then x minus 4 with multiplicity 1. So the only multiplicity bigger than 1 was this 3. Now I want it to pass through 0, 4, so I'm going to put an a in front. And now I can solve. I can put a 4 over here and a 0 in for x. And then it's just a matter of carefully doing this multiplication. Now notice what we have. We have 4 equals, let's see here. We've got, this is positive 9 times 2 and then 3. So let's see what we've got. We've got 9 times 4. And this whole thing's going to be negative, right? Because we're going to have one negative. So we've got a times 2, and there's 9 times 4, which is going to be 36. Okay, so I just multiplied everything out. Now notice it was going to be negative. I determined that at the beginning because this is squared and we just then have one negative. Okay, so let's see what we can do now. We've got 4 equals negative 2 times 36a. And notice I can divide out the 2 here. Okay, so now let's see what we've got. We've got 2 equals negative 36a. And now I'll go ahead and divide. I get negative 2 over 36. Okay. So there's what our a is. And I guess that will divide into negative 1 over 18. So we get a equals negative 1 over 18. Yeah, that's it. So that's what goes right here. Okay, now let's look at some more here. Let's bring in some complex numbers. Okay, so now let's just come up with a polynomial with these complex zeros, or 3i, non-real, negative 3i. Well, let's see what that would look like. That would be f of x equals, and now it didn't tell us any particular point to make it pass through. So, we can do what we want. So I've got x minus 2, x minus 3i, and x minus a negative 3i. Now I just multiply this all out. So let's see what we've got. We've got x minus 2. If I multiply this out, notice this is x minus 3i, x plus 3i. Well, that's going to be the first, this is a difference of squares, right? Or, well, look, we've got this situation where if we do a minus b times a plus b, we get a squared minus b squared when we multiply all that out. Well, it's going to work that way here. We've got x squared minus 9i squared. Now let's see what this is going to be. This is going to be x minus 2 times x squared plus 9. Because dig this I squared, anytime you see an I squared, you can replace that with a negative 1. So we've got x squared plus or minus a negative 9. So that makes a plus. And then I just multiply this out. So here I go. I've got x cubed plus 9x. So just distributing like this. Minus 2x squared. And then minus 18. So here is the polynomial that I wanted. I've got x cubed minus 2x squared plus 9x minus 18. There we go. So that's the polynomial with these zeros here. Now, let's look at one that's a little more involved. Here we've got non-real roots, 1 plus 2i, 1 minus 2i. Now remember, these non-real roots like this, they always travel in conjugate pairs. So if if 1 plus 2i is a root, then so is 1 minus 2i. But here's what we've got then. We've got x minus 1 plus 2i and x minus 1 minus 2i, and then x minus 2. See? I knew these were roots, so x minus each one of them, that's a factor. Okay, now, I need to multiply this out, and the trick I like to use is this. I like to do a little regrouping. I like to take this x minus 1 here and this x minus 1 there, kind of pull those out. So I've got x minus 1 minus 2i. See? Notice I just cleared my parentheses. I'm going to do the same thing for this next one. I get x minus 1 plus 2i. There, see? Put these two minuses together, you get a plus. Now, the reason I did that is because dig what I have here. I have x minus 1 minus 2i times x minus 1 plus 2i. Well, that's like that difference of squares thing, and I can rewrite this as x minus 1 squared plus 4. See? I can do the same thing as I did up here with this one. Okay. Now, I'm still not done because I have the x minus 2 here, and I need also to clear this parentheses here. So let's see what I've got. I've got x squared minus 2x plus 1 plus 4. See? I just multiplied this out. Now, if I add, like terms, I'm going to get x squared minus 2x plus 5. There. Okay. Now there's no more of those i's in there, so I'm just going to multiply. I've got x squared times x. That's going to be x cubed. X squared minus 2, that's minus 2x squared. Okay. Then negative 2 times x, that's negative 2x squared. And negative 2x times negative 2, that's positive 4x. Okay, now I'm on the 5s. 5x minus 10. Okay, so let's see what we've got here. We've got x cubed minus 4x squared plus 9x and then minus 10. And we're done. Okay, so that's the way we would do that. Okay, now we go down to this next one. It says find the missing roots if x equals negative 5 is a root. Well, the way we find the missing roots is by dividing. So if x equals minus negative 5 is a root, then x plus 5 is a factor, and I want to divide that in to find my others, my other roots, or my other factors first. Okay, there it goes. Oops. So if I tell you 2 is a factor of 6, you can divide 2 into 6 and get 3. Well, that's what I'm doing here. I know that x plus 5 is a factor, so I divide it in here and find the other. So x will go into x cubed, x squared times. Now multiply. There we go. See? Now subtract and bring down the next term. Okay. Now x will go into 2x squared, 2x times, and then multiply. So there's 2x squared plus 10x. Okay. And then I subtract, and it looks like I get a negative 27x. And then I bring down the negative 15. Okay. Then I divide. X will go into negative 27. X negative 27 times. Okay. And then I get negative 27x. I'll look at this. I messed up here. 5 times 27. Well, what is that going to give you? That's going to give you, let's see, about 135. Well, you're not going to get a zero remainder. So what happens when that happens? Apparently I messed up here. I said find the missing roots if x equals negative 5 is a root. Well, apparently x equals negative 5 is not a root. Now, unless I did something wrong here, I don't see anything. Well, so when this happens, okay, if you're taking a test or something and this happens, here's what you need to do. Just go back and very carefully look at your work here, and maybe you did something wrong here, but here's a quick way to test it. I claimed that x equals negative 5 is a root. Well, let's try it out. Let me plug back into this thing. I'll get negative 5 cubed plus 7 times negative 5 squared minus 17 times negative 5 minus 15. Now, that needs to turn out to be a 0 if indeed x equals negative 5 is a root. So let's see here. Let me calculate it here. I've got 7 times negative 5 squared, okay, minus 17 times negative 5, and then minus 15. Let's see. Ooh, I think I get 120. And if I did that all right, yeah. So that's a problem. So yeah. So let this be a lesson. If you don't have a zero remainder, then yeah, that's not a root. And if you're asked that on a test, the answer would be you would go through and show this work, and then you would say, well, it's not a root because there's not a zero remainder. Okay. Now let's look at this next one. maybe this one will work. Now, this time I'm telling you x equals 3i is a root. Now, you know that if x equals 3i, you know if that's a root, then x equals negative 3i is a root. So what you want to do is you're going to divide into this to find the other. But what are you going to divide? Well, you're going to go ahead and multiply out the factors that you know. So this is going to be x squared plus 9. X squared plus 9. That's what you're going to divide. And you're going to divide that into the original up here. So x to the fourth minus x cubed plus 7x squared minus 9x minus 18. Now, hopefully, I've put one together that, does in fact work out. Hopefully, x equals 3i is a root. That was my intention anyway. But anyway, the process is the same no matter what. You x squared into x to the fourth. Well, that's x squared. Okay, now let's multiply. We get x to the fourth plus 0x squared. Well, 0x cubed actually. And then plus 9x squared. Okay. Let me double check. Yeah, okay. Now, we subtract, so this is going to be negative x cubed. This is going to be minus 2x squared. Okay. Now I'm going to bring down the negative 9x. X squared will go into negative 3x cubed, negative x times, and then I multiply. Okay, so I get negative x cubed plus 0x squared minus 9x. Okay, then I get negative 2x squared here. This is 0. And I've already brought down the 9, so let me bring down the negative 18. Okay, now x squared will go into negative 2x squared, negative 2 times. Okay, now let's multiply here. So we get negative 2x squared minus 18. Oh, look at this. No remainder. Hot dog. I got one that works. This is what you want to happen whenever, if you're told something is root and you divide, you want to get a 0 remainder. So here's what we've got now. We've got x minus 3i, x plus 3i. Okay, there's two factors. Now let's see what we've got here. Times this. This is our polynomial right here. I wonder if this could factor more. Well, let's see here. We've got x minus 3i, x plus 3i, and this is going to be x plus 1, x minus 2. Yeah, there we go. So look what we have. We have the following roots, plus or minus 3i, negative 1, and positive 2. Okay, now let's look at this. Let's look over at some rational functions. So we want to find all the intercepts and asymptotes. Well, so to find the y-intercept, same way as always, you're going to put a 0 in for x and find out what the y is. For the x-intercept, or sometimes intercepts, you're going to set the top equal to 0. Okay, so we've got negative 2, 0. Now remember the horizontal or the vertical asymptote, we set the bottom equal to 0. To get the horizontal asymptote, we use the cases. Case 1, the degree on top and the degree on the bottom are the same. So the asymptote is going to be the ratio of the leading coefficients. Okay. So that's a quick rundown on, how we would deal with this particular problem. Look, here's another one down here. Y-intercept, same way. We've got 0, negative 1/2. See? Because we put 0 out the x's and we just got 2 over negative 4, which is negative 1/2. Here's the x-intercept. We set the top equal to 0. So we get negative 2, 0. Now the way we get the x-intercept is we set the whole function equal to 0, but in this case, it just amounts to setting the top equal to 0. Now, as far as the vertical asymptotes, we've got x squared minus 4 equals 0. That means that x minus 2 times x plus 2 equals 0. I just solved this one by factoring. So we get 2 vertical asymptotes. 2, negative 2. 2 vertical asymptotes. Horizontal asymptotes. Well, the horizontal asymptotes, this is the case where the degree on the bottom is bigger than the degree on top, so it's y equals 0, or in other words, the x-axis. Okay. Let's look at another one here. We've got another rational function. We've got the y-intercept. Looks like we're just going to put a 0 in for x, and we get 10 over negative 6. Okay, so that's going to be 0 and negative 5/3. Okay, that's our y-intercept. Now, as far as the x-intercept, we set the top equal to 0. And you can factor it if you like. So we've got, here we go, x plus 5, x plus 2. So we get negative 5, negative 2. These are the x-intercepts. Now, as far as the vertical asymptote, we set the bottom equal to 0. We get x equals 6. Now for the horizontal asymptote. Whoops. Degree on top is bigger than the degree of bottom. No horizontal asymptote. So we need to find a slant asymptote. And remember, the way we find the slant asymptote, we divide. And the remainder is the slant. So x will go into x squared x, then x squared minus 6x. This is going to be 13x here. X will go into 13x 13 times. Oh, I forgot to bring down the 10. Let me bring down the 10. Now 13x minus, is that 78? Let's see here. Yeah, I think so. Okay, now we're going to have a remainder here, but we don't care about the remainder. I ran out of room. I guess it's 88. But here is the slant asymptote. The slant asymptote is going to be y equals x plus 13. That's the slant asymptote. Remember, we don't care about the remainder. That remainder just goes to 0 as x goes to infinity, so we're not worried about it. Okay, now on to the inequalities. So we have this higher order inequality. We have this polynomial inequality. Remember what we do. We find where this is equal to 0 and we use that as a boundary point, or boundary numbers. Well, we get negative 3, 1, and 4. See? I get the 4 from here, the 1 from here, and the negative 3 from here. That's what will make this 0. And then I pick test numbers in each of these regions. I pick a test number less than negative 3, which is negative 4. Yeah, that's one of them. Something between negative 3 and 1, maybe 0. Between 1 and 4, 2. Something bigger than 4, I'll pick 5. And then we test those. We plug them into the polynomial. So we got negative 4, 0, 2, and 5. And I'm going to test those into x minus 4, x minus 1, and x plus 3. Okay, so here I go. I put in the negative 4. Well, this first one's going to be negative. See if I put a negative in there. This one's going to be negative. And all three of these are negative. So this right here has a negative value for anything less than negative 3. So I'm going to put a negative there. Now remember, we're looking for where we have a negative value. Now I'm going to put in a 0. So I get a negative, and a positive. Two negatives make a positive. So it's above the x-axis there. It's positive. Then I put in a 2, and I get a negative, a positive, and a positive, which gives me a negative. And then I put in a 5, and I get positives across the board. But our solution is going to be wherever we have the polynomial less than 0. Well, that's going to be here, negative infinity to negative 3, union with 1 to 4. And notice I don't include the endpoints because this is strictly less than. Okay. Now let's look at the next one. The next one, to find the boundary numbers, we've got to factor. See? So I can factor this a little further. I'm setting this equal to 0. I factored a little further. Okay. And now we've got our boundary numbers. Dig this. We've got 0. Well, let me do this. 0, negative 2, and negative 5. There we go. See, I get the 0 from here, the negative 2 from here, and the negative 5 from here. And then I test values. Yeah, I'm going to test those 4 values the same way I did previously. And I will look at the factored form, right? So it's x plus 2, and x plus 5. So here I go. Negative 6, negative 3, negative 1, and 1. Now, if I put in a negative up here, this first term is definitely a negative, or the first factor. This one's negative, and this one's negative. 3 negatives. So it's negative over here. Now, if I put in the negative 3, negative, negative, and positive. That one's positive. Okay. Now, if I put in the negative 1, negative, positive, and positive. Negative. Now, I put in a 1, everything is positive. So this is positive. Now remember, we want it greater than or equal to 0. So I want between negative 5 and negative 2, including those numbers, unioned with 0 to infinity. I never include infinity. Just put a parentheses around it. So there's the solution region for that inequality. Okay, now I want to go down to a rational inequality. We still find the boundary numbers. I want to find out where the numerator is equal to 0, and I get x equals 1/5. But additionally, I want to find this special boundary number where the denominator is equal to 0. So I get x equals negative 1. Now, you have to be careful. Never include this as part of your solution, because that will make the denominator undefined. So we have to be careful. Now, we don't really in this case, because this is just strictly greater than 0. We're never going to include the endpoints anyway, but you have to be careful of that. So here I go. I've got -1 and 1/5 here. So I'll pick test numbers like -2, 0, and 1. I'll just pick those test numbers and plug them in just like usual. Okay, so I've got -2, 0, and 1. Okay, so I'll just plug those in. Now, if I put in a -2, notice the top is negative and the bottom is negative, so I get a positive. See? -2 up here gives me a -11, and then over -1. So that makes a positive. Now, if I put a 0 up top, I get a negative up top, positive on the bottom. Well, that's a negative. And what about a 1? Well, I get positive on top and bottom. So here's the way it goes. It goes positive, negative, positive for this one. Okay. And we want where it's greater than 0. So it's going to be -infinity to -1, unioned with 1/5 to infinity. Okay. Well, that's some practice, just some random polynomial and rational function practice to get you ready for an exam.